little bit change the position. So each part of the story would be generalities about elliptic classes and elliptic genus also, because I think this is not very well known for most of you and very few people working, not only here, all over the world. There are very few working on elliptic characteristic classes, but they appear in this story of Okunko and Segu and Velos. And I was using elliptic genus, elliptic characteristic classes for a while, something like maybe it's even 10 years already. And there was some box there, Jacobi theta function, which I treated so far as a black box. I know that it exists, no formal properties, but I have no courage to enter the box because it's people from more than century were studying the theta functions, and a lot of number theory was involved. So I just took it as a given, God given, or I don't know, Zagier given element. And now I just tried to open the box, and a lot of things came out which are not very scary, and I think it's worth to say a few words about this. Okay, and I have very few transparencies, so maybe I would write some parts on the blackboard. Okay, so my motivation is that Chern classes and motivic Chern classes are not appreciated by hardcore algebraic geometers, those working on minimal model program or working on birational geometry, because they use resolution. They have divisors on the resolution, and this divisor has some coefficients. And in our story, divisor is just a subset of variety. We just ignore the coefficients that appear. On the other hand, in this birational geometry, these coefficients are crucial for discrepancy. And okay, so I cannot use every singular variety. I would use, for example, for the being normal variety, they have a canonical divisor, which is a valid divisor. You can say you take a divisor on the smooth part, section of the canonical bundle. Canonical bundle is just the top exterior power of the cotangent bundle. You take a section and you close it. And it's a normal singularity, so there is well-defined divisor up to linear equivalence. But it is of homological nature. It's a divisor. You can push forward it, but you cannot pull back. So assumption is that singularities are Q-Gorenstein. That means not this canonical divisor, but it's some multiple can be pulled back to a resolution. Okay, and you pull back this divisor to the resolution, and look what is the difference between canonical divisor upstairs and the pullback of that one. If there is quality on the node, then you are very happy. You say that's a crescent resolution, and basically all what you want to know about what is downstairs, you deduce from the resolution. There's no divisor. For example, Hodge numbers are the same for any crescent resolution. But in general, there is this discrepancy divisor, and you want to introduce some correction to formulas for the characteristic classes involving this divisor. Okay, I'm going there. Okay, but if you have two resolutions, you can always find a third resolution that dominates both. So if you study the dependence on some notions on the resolution, it's enough to consider the case when you have just one resolution dominating another, and And as you know, it's enough to consider just a blow-up. The smooth center well fits to the divisors. So, okay, so you just should see how the divisor E is transformed from x to x prime by this formula. You subtract from the canonical divisor, you pull back, and then you go back. Okay, and suppose you know the coefficient. The goal is to define invariants of y, knowing the Chern classes of the tangent space of the resolution, knowing the homology classes of the divisors, and also these coefficients. And from that formula, this is relevant the following notion, called canonical pullback. I use this phi, not upper star, but some k. But this is my notation just for this lecture. So having any divisor on a smooth variety and a map, birational map, you just pull back in this way. You can say somehow you dualize, shift, pull back, and redualize, and dualize again. Okay, and the goal is to define some characteristic classes. And I'm back. What I would further make precise. I define some characteristic classes for the smooth variety of the divisor, which is defined for the smooth varieties with simple normal crossing divisor. And I would say that this class is invariant with respect to canonical transformation. Canonical transformation is taking a pullback of the divisor, computing this invariant, and pushing down. So this is crucial. If I have such a way of defining characteristic class, then I'm happy because I can say that this class does not depend on the resolution. And as a core, somehow you can just remove singularity theory from the old story. Instead of a singular space, you look at some system of resolutions. On each resolution you have divisor, simple normal crossing, and also maps are generated by the elementary blow-up. So somehow you can forget about singular space, but we will not.
Is this exactly the notion of K-equivalence, or it's only similar?
I'm not sure. Maybe. Okay, so for some time we will just deal with non-singular variety, but with a simple normal crossing divisor with interesting coefficients. And coefficients in general are rational numbers. Also, you can extend the definition to the complex numbers. All the formulas will be plugging numbers to some holomorphic functions. So if you know how to plug in rational numbers, then you can plug in any kind of number, except that these are not holomorphic, would be meromorphic. There will be some poles. Okay, so how you define characteristic classes? Kirchner says that having a formal power series f of x starting with without constant term, you can build a some characteristic class. I'll already skip to this form. So how you, maybe now I would use, I would keep this notation. So you have f x h, and I would also multiply by x here. You can think about it as a x divided by f of x times f of x plus h times this, and inverted there. So this you don't care, this is normalization. So this looks like a Todd class. And this is Euler class, Euler of the bundle. Here the X is like stands for the first Chern class, so this is for the bundle L tensor with character CH. And H is a formal variable, so this is what already appeared in in Leonardo talk. So somehow you can think, so you want to compute the Euler class with respect to some cohomology theory, Euler class of the bundle, so maybe from line bundles I pass to the any rank bundles. But instead of Euler class, I compute twisted Euler class by a formal parameter. So it's like a Chern class of E. And I compute it in some cohomology theory related to a formal power series E. This F stands for the Euler class of the. And then we have Riemann-Roch that if I go to usual cohomology, I just have to, if I want to push forward, I have to correct by this step. Okay, so maybe I would, so this is.
But in the middle one, it shouldn't be a line bundle.
Reply to the Chern roots later.
I reply to the Chern roots. So it's the other point.
In Leonardo's talk that came up in this example of the self-intersection formula, uses a C-star equivalent, that is the H or character of
Well, that I understand very well, but if it was not a line bundle, then it's different. Yeah, we have to apply for the roots.
Yeah, you apply for the roots, but so this is function, and this function represents, stands for the characteristic classes. And if you take a function 1 minus e to minus x, then you get exactly the Hirzebruch class computing chi genus, except that you have to make this substitution that y is too many minuses, but this is how it is. Okay, so this is how you define this formal power series. It has a pole, so this hx in the denominator, and here is an invertible factor. So if you knew that your tangent bundle, the direct sum of the bundles divided corresponding to the divisors, then you would use this formula for the Chern class with boundary condition E. So if AI was 0, that means no divisor, the coefficient 0, then it would be just plugging here H. And this formula is okay if you look locally, because locally at the point when the divisors cross, you have maximum number of the divisors crossing at the point is equal to the dimension. Okay, and this formula works locally, and not locally you have to produce such a formal thing that first you compute this invariant like there was no divisor with Chern roots, then divide by the classes corresponding to the components of the, you just exchange the classes of the divisor by these classes of the divisor modified by the coefficients. So you have such a...
In the middle formula, what is EI?
So it's here. EI is a class of the divisor. Also in this formula it is the same as the Chern roots. Because if the divisors cross, then the Chern roots are just the classes of the divisor. So you can think of it that you have this formula, like here, but you introduce some coefficients corresponding to the divisors in the point where the divisors pass. Okay, so this is the definition. This is general, no elliptic functions so far, and elliptic function will just appear.
The important point is, of course, that the second piece comes from your divisor, so that is a non-classical context. So everything depending on E, so the right half of the formula.
what you call classical context.
Hitzebo's context of just boundaries or tangents without the divisor on the space.
Yes, so this is, you can say,
That is like Hitzebo in a slightly different
and
language.
this is maybe I should say now that this is the construction of Borisov and Weber, just to modify this coefficient. I mean here, maybe this is the main formula that you use in local computation, but this local computation is fine because there is a global formula. Okay, but let's forget about Anatoly and Borisov. Just ask yourself, given a function f, is this formula invariant with respect to canonical modification and canonical transformation? And this is a theorem which is easy to prove, but except that you have to differentiate 6 times. But you will see the proof. Maybe I would not perform that computation. So this is what is interesting for us. You have function f, and you ask yourself whether this formal series f defines a well-behaved with respect to the canonical transformation. So that means that this function defines an invariant of a singular space, again having Schubert-Einstein singularities, and there are some extra conditions that I will now do not show. Canonical transformation, and the basic map that you know is the blow-up. So take C2, this is a plane, and you blow up origin. I don't know how to draw it, but the divisors are important. I don't have red color. So there are 2 divisors downstairs. And if you blow up, they are disjoint. But you have exceptional divisor. And if you, maybe I would be smart in the beginning. Instead of coefficient A, I would have a coefficient A plus 1 here and B plus 1 there. Because I would subtract 1 in the. And so if I pull back, so that I have A plus 1, here I have B plus 1, and here on the exceptional divisor, if I just pull back, I would have A plus 1 plus B plus 1. But canonical divisor enters, so you, yes, and if you do the calculation, this is A plus 1 plus B plus 1. So instead of coefficient A, you use this coefficient shifted by 1. Okay, and I use equivariant cohomology, of course, and I compute the.
I don't see how.
Okay, you have to know what is the coefficient of the canonical divisor pulled back to the resolution. So you ask, take a volume from here, pull back there, and ask what is the order of pole along the exceptional divisors. Also 0. It's 1.
It is objective to the equal sign.
Where?
Purple line.
A plus 1 plus B plus 1, and then A plus 1 plus B plus 1 minus.
Aha, okay. Okay, but I have to subtract 1.
Yes.
Yes, I said that. I said that, but I didn't write.
And that -1 is coming from this
From the divisor.
discrepancy. Yeah. Okay.
From the whole of the, even you can say for the undergraduate student to take form dx with dy, you make a substitution and you ask what is the order of the pole. Okay. So that's why. Okay, I use A and B, and instead I should use in that formula H multiplied by A plus 1 minus 1, which is H. So I just forget H and I using localization formula. You have this quality. You want to have it. So if the power series defines an invariant class with respect to the canonical transformation, this should be satisfied. So from the general, I talk about all the manifolds that are in the world. I just take a test case, just blow up of the plane. So it's miracle that this already gives you, I think, complete answer.
But where did you find the H again?
So H is in the definition.
Yeah, but not in that line. So where is it?
The notation is short.
Okay, I just
Say it in words. So A stands for A plus H.
yes.
Ah, okay.
No times H.
Also.
Times H. Anyway, you with Tarasov and Barchenko do not use H. You have new variables called new, I guess.
Depends.
But this is nothing, no topology, no algebraic geometry. This is just a statement about power series, and I say that so you have capital F and small f, and I say that of course f can be also written. Maybe I will use this. F of x can be written x times x of g of x, and the g you want that at 0 is 1, so g has no constant term. So you write f in that form. Also, I want to subtract the first two terms, lambda mu, which have different row. So I assume that this g, of course, vanishes, its derivative vanishes, and second derivative vanish. So I claim that this, when it's written in that form, the function g satisfies this differential equation. And I ask people who are working in differential equations, do they know it? They didn't see such equation, so I just played with that equation. But on the other hand, we already know the solution. The solution is the theta function, Jacobi theta function, which will appear later. So Jacobi theta function does normalize because the derivative is 0. It's a solution. And I claim that every solution is of that form modified by the factor. And Jacobi theta function can be expanded in the modular forms. And I would give 2 slides about modular forms.
Of course, one should emphasize, we came to this functional equation because we are interested in blow-up relation, because it comes from big factorization that controls all.
Yes.
So that is a geometry input.
Yeah, but maybe the story it goes like this, that Borisov and Gober defined an elliptic genus, and they had to prove it, and they proven using quick factorization, and also reducing everything to the toric situation. So it was also elementary calculations, maybe statement about the functions.
Yeah, but I want to emphasize that this functional equation, the differential equation you get, is not classically studied, because going to the blow-up relation is not what people classically have done. So this is this new viewpoint going to.
Yes, although Borisov and Gober use quick factorization.
They don't use this language, and this is of course
They
better language.
They
This is
didn't
much
use
better language.
localization. in fact.
But to look at kind of differential equations or properties, and here it was started to go to rigidity questions of elliptic genus.
Yes, so this
It
is,
also reduces to equations and so on. But these people don't look at the blow-up relation.
they
this
were
is
looking for this spin boundary.
I think that is a new viewpoint coming from this
Spin
new
line from boundary.
geometric thinking.
I really don't know, because there are so many things that seem to be always in the around, but maybe they some pieces that were not put in that way, so I don't know. But anyway, it was amazing for me, just playing with this differential equation. Also because I didn't solve any differential equations since I was a student.
It looks like a degree 4, but it's really a degree 2 equation, right? Because there is no G and G prime doesn't appear.
Yes, and maybe it would be visible in the next slide. Why this do not? But maybe okay. Okay, so I repeat the blow-up relation. And okay, so this is what I written here. And the first reduction, I can assume that the function has no. Okay, maybe I should say why I'm not interested in the factor. Okay, maybe now I need to erase it. Okay, so I do it this way. This is f plus x plus h divided by f of x, f of h, and plugging in that, I have x plus h, x, h. Then there is x of okay. So if I modified it by e to x plus h, e x, e h, so that would cancel. Yes. So artificially, even if the function has a second derivative, non-trivial, multiplying by a factor, I have g of x, I can create g tilde of x times e to times oh, I'm talking about f. I'm talking about f. Okay, and this slide, if I take f of x and I multiply it by e to x with some parameter, so then it would not affect the function that I'm interested in. So that's why I can just cancel the quadratic term. And if I cancel the quadratic term, then I claim I skip the point that all the function is odd. There are no even exponents. So if you assume that the function is odd, function f is odd, so that means that g is even function. Just differentiate 6 times the formula, that one. In fact, you take a numerator, you just find a common expression, just a quotient, and take a numerator, differentiate with one variable, second with x, a, and b twice, and then plug in 0, you have function in one variable x. Originally, it would appear g of x and g of minus x, but if you know that the function g is even, you have just equation in one parameter x. Okay. Okay, so let's assume that the function g is of that form. This is the equation, and if you expand it, so miraculously it starts with power 6. So no dependence of a2, the second coefficient, and also a2 does not appear further, only appears a4 and a8. And the rest can be computed in these terms. Maybe I go to the solution. Solution is, you can take three coefficients arbitrarily, A2, A4, and 6, and the next coefficients depend on A4 and A6 in a polynomial way. So this is what just can produce in one line in any calculator, any package with algebra. Okay, but you know that these coefficients are coefficients that are the same. I mean, these relations are like for the coefficients of theta functions, which are exactly the modular forms. So I move further. So this is the theta function. This is, I recall the definition, although maybe it's really irrelevant. If you normalize, this is x and times x of g of x, and g of x has this coefficients which are modular forms exactly, and there are some coefficients just to keep the notation from Zapier. And so this is the corollary. The general solution is that of the form. So you can say that the solution is like elliptic genus, but perturbed by this factor. But as I said before, this factor lambda is irrelevant because it cancels out. And in the formula for the function f appears just x linearly and h linearly. This is a quadratic form associated to this quotient of theta functions. So you get a corollary that you have perturbed elliptic genus that can be just defined for any Hugo-Renstein singularities, and plus you need this Kawamata log terminal condition that the discrepancy coefficients are greater than -1, otherwise you may fall in some contradiction. But I have no time to expand this. So I should say a few words about modular forms. So this is a classical definition. Oh, so this is not f. This is f. Has nothing to. This f has nothing to do with that f. The function f is a modular form. It's a function on the upper half space for the imaginary part of complex numbers greater than 0. And it's a holomorphic function that transforms in that way. And there is some condition.
But you assume all coefficients are integers.
Yes. So these are SL2Z acting on the of course, finally you want to have something depending on the lattice of this transformation.
How can it happen that there is no A and B on the right?
Just like this.
So this arbitrary, you change it. You choose any A and B.
No. From SL2.
If it ABCD is a matrix in
It's a matrix in SL2Z. If you divide the upper half, then you get a Riemann surface, and that corresponds to the differential form of order k on the quotient Riemann surface.
But there is something what you said, that from that you see that there are no odd modular forms, because this would mean that f of z would be minus f of z. Okay, and so these are examples, such a Eisenstein series, and we need a normalization. You multiply by something, and then you get some expression with almost integer coefficient, except the first one when you have Bernoulli number divided by 2k. And the important theorem is that the ring of modular forms are generated by just two modular forms, G4 and G6. This is in every classical book on modular forms. This is one of the main points. But, or maybe I'll go back here. if you look at this formula, it appears then go back. It appears here, so G2 also appears. And so you have G2. But this is somehow anomaly. This is singularity in the whole world, not in the particular variety. It's a singularity in the whole system of things. So this is something that you can define by the same formula, except that it's not modular form because you have some correction there. So this is something causing problems that further, if Borisov and Weber compute this elliptic genus of a manifold, any complex manifold, compact complex manifold, integrating, you get a function on tau and h, and this function is not does not have a good transformation property unless you have Calabi-Yau manifold. So this irregularity of G2 causes that non-Calabi-Yau manifolds have some bad properties of elliptic genus.
So this is, in your language, the analog of what Totaro was figuring out, that if you go to rigidity of elliptic
Yes.
genera,
Also,
you should ask the fiber should be Calabi-Yau.
yes, it appears everywhere.
Okay.
Okay, and maybe what I have here, maybe it's another, but maybe coming back to that, you can now, having this modified elliptic genus, you can somehow kill this G2 application. So you can have characteristic classes that have better behavior. And there's also another thing. If you take this modular form, this particular combination is modular form of weight 12. This is a graded ring. And this nowhere vanishes except Q equals 0. So somehow you cannot make this coefficient 0 in your series. But with my modification, you can plug in all the modular forms equal 0 except the coefficient at x squared. So gives you, it provides a new characteristic class. Okay, so let's move. Okay, and how much? 20 minutes. Okay, I wanted not to extend. So now okay, you have full generality of this elliptic genus, and now let's, in fact, you have three coefficients that are A2, A4, and A6. And you can do whatever you want. If this were just modular forms, they are depend on one parameter. But now you have three coefficients, and you can do different things. But let's stay for the moment in this elliptic. So I would was already in the Borisov and Weber first paper on that. So if you go with tau going to I infinity, that means Q going to 0. Q is always x of 2 pi I tau. So let's see what happens. So there is a nice expression for this function that is relevant for us. So there's rational part, and AB just plug x. So that's why it's better maybe to do it right from the beginning in the case theory. So just like with x. And then you have some number theoretical things, but with exponent with coefficient q to n, and you plug in q equals 0. So this cancels. You have such a characteristic class. And so then, for example, it follows that if y, the singular thing, maybe I should keep this notation all the time because I do not repeat it. But all the time you have y, which is singular, q Gorenstein, and here is resolution, which is called psi, and I make a computation here and push forward there. Here you have maybe sometimes divisor D and then the divisor E. So you compute something upstairs, push forward, and that's why, because this function is invariant, creates a class invariant with respect to canonical transformation, you get something that is well defined for the singular space, and this is exactly ky genus, except that it's
This is standard normalization.
standard or non-standard, I don't know. You have to get
Oh, in the elliptic genus, this other factor is always coming in from.
you have to get rid of this factor. And also, when I started to work with that, I was interested in quotient singularities. So D4 is the case of the quotient of C2 by some bidihedral group, and you can compute maybe not a global elliptic characteristic class, but its localization to a fixed point with respect to torus, C star. If you have quotient singularity, so this is Cn with action just by multiplication of the C star, and if you act by a group linearly, so the action survives in the quotient. And I look for the was work with Marysia Dontenbury. She was more computer-minded person and just had in her notebook maybe not 100, but many examples of the subgroups of SLN-Z, or also symplectic very often. And it was her PhD thesis to compute something in this world of birational geometry. So just applied the computations, and we did a lot of experiments. But anyway, I just wanted, there was something said about the D and or before singularity. So you have one component, so this is a resolution. If you resolve, you have one component which is fixed by torus, and three components, this is with some torus action. These numbers are the weights of the action, like in GKM graph. But also you need to know what is the weight of the transversal direction at the other fixed point of P1. So this is 4. And knowing these numbers, you just can compute local elliptic genus. So 3 components, 4, and here -2 because you other direction. And also you have to integrate this one. And integration is like taking residues, and you get a formula which the limit is something that, in fact, up to this modification, the Moline series of the function of kind of Moline series of the local ring, modified because you have parameter y. If y equals 0, it would be just a functions, and now also I take into account the forms. Okay, so this, anyway, to make it short, this degeneration gives you something of the Hirzebruch, this is local Hirzebruch class of this singularity.
So you realize D4 in SL2, yeah?
Yeah, that's
So
well
that
the
means-
Kleinian group.
Yeah, so that means this elliptic localization should also fit with Mackay correspondence.
Yes, yes. So this was motivated by the paper of Borisov government, but because you can also compute it just looking in terms of representation.
Yeah, since we had Mackay correspondence in one of the other talks, so elliptic was also some versions of elliptic classes were designed to fit with
Yeah. So
Mackay
the
correspondence.
theorem was that you can define equivariant elliptic genus using group action. You have to look at all the fixed points of pairs. If you have two commuting elements G and H, you look at the points that are fixed by two commuting elements, and gathering all the invariants of these fixed points, you can cook up some characteristic class. And in fact, they were only interested in genus. So they integrating upstairs. This is the same as computing the singular elliptic genus downstairs. And the theorem is that the equivariant is equal singular of the quotient. But too much to say. I will not. I have some other. Also, if you go with Q, so I want to convince you that this elliptic genus contains a lot of information classically studied by so many people. So if you go with Q equals to 0, but you suppose that this ambient space Y is smooth. Also, it could be singular as well, but for simplicity, assume that it's singular, but the divisor is singular. You take a log resolution of the divisors, and you upstairs you have elliptic genus, and take the limit with parameter tau going to infinity. That means Q going to 0, and then you get Hodge theoretic zeta function. Up to this factor as always. And Hodge theoretic zeta function, this is formula by Denef and Lozé, that you take this exceptional divisor, you cut it into pieces, into stratification, locally closed stratification. You compute some invariant, in this case, chi-y genus with minus h. Compute invariant of every piece, and this piece is counted with such a multiplicity. This is some formal expression. And here appears discrepancy that we just was talking. So the log canonical threshold is the minimum of zeros of the quotient. So what is this? If you pull back divisor, it has some multiplicity upstairs. And also on every divisor. And also there is a pole of the Jacobian, and you already include I plus 1 in the definition here. Okay, and the statement is, maybe it was known by some, but Weber.
This was earlier. This goes back to Batyrov.
Batyrov was doing stringy invariants, and instead of this, he took the Hodge polynomial. So chi-y is less than Hodge polynomial.
Yeah, but chi-y is the only one that fits with both, with elliptic and with Hodge.
So this fits to, so this is somehow specialization of Batyrov. Okay, and if you degenerate with y going to 1, you have topological characteristic, and this topological data function that appears in example in works of Limweis. He confirmed that my computation fits to what he has in his computer, and he's one of the computation, of course, cast. So this is a graph resolution. So this is not a dual graph. These are just the curves, and the fixed points. In red, there are fixed points of the torus action, and this is all the component of the fixed point. And I apply the localization formula. You have some part which is just plug-in function f, this one. Aha! But here I applied multiplicative notation to save the space. Instead of writing, for example, here t minus u, I write t divided by u, and instead of writing 5 plus 6s times h, it's more convenient to use. As I said, everything comes from k-theory. And here this is the final answer. This is topological zeta function, but it's a global topological zeta function, not a local. You cannot localize elliptic genus. That's the disadvantage. Okay, and what now? And this degeneration. Also, you can put coefficients tau in front of the divisor and see what happens. And the clue is that if you look at this expression with tau going to infinity, and the tau is involved also in the coefficient, then some round down or round up, depends how you write it, appears in the formula for non-integral coefficients lambda. And this way you can obtain new characteristic classes and application to stable envelopes, and already it appeared in some form in the work of Richard with Tarasov and Warchenko, this deduction from the elliptic stuff to the case-theoretical one, and maybe with Jakub we made it more general. We defined a twisted motivic Chern class. So the setup is the following: that you have some singular variety, but you assume that the singularities are contained in some subset called boundary. Like Schubert cells, you have open Schubert cell and its boundary, and singularities are in the boundary. So outside the boundary, everything is smooth. And you have a divisor, which is Q Cartier divisor, but you can make that support lies in the boundary. And then you can twist the definition of the motivic Chern class. I don't know, there was no formal definition of the motivic Chern class in this conference, but I will not make it now. So you resolve.
The symbol was used. I used the symbol at least.
Yes. So you compute motivic Chern class upstairs, you take a divisor from downstairs, you pull it back, and then you take a roundup, multiply motivic Chern class by this. So this is in case theory written. You multiply by the class of that, and then push forward. Okay, and of course, as always, we assume that the resolution is simple normal crossing. And if you consider this definition, on one hand, the elliptic genus degenerates to that formula. On the other hand, there are no restrictions here for the singularities, so this is advantage. And the theorem that we've proven that this definition does not depend on the resolution. And what? I think this is the next slide. So it can be applied to. I was stupid to give it in the abstract of my talk that I will talk about Schubert classes, but anyway, you can define stable envelopes generally for Białęnicki-Birula decomposition, and the theorem is the stable envelope that depends on the bundle L of the line on a line bundle L, and if this line bundle L is small and negative, small ample and minus L is ample and negative, then we obtain usual motivic Chern classes. But our theorem with Jakub is that in general you obtain the stable envelopes are the same as the twisted motivic Chern classes for any line bundle. And this has an application to Schubert's stable envelopes of Schubert varieties, and you have this. You can extend the standard gadgets like the Mazur-Lushkin type operators with parameters. And maybe I think this is last slide. You can take this unlegal degeneration that you keep A2 non-zero. With this, maybe this is convenient to have 2h in denominators, and you take these two things zero, the further coefficients, and you get another thing. I computed a toy example. You have P1 with divisor D with some coefficient, you get such a function. So this is homework to check what you get for Schubert varieties in general. So it's just rational formulas, and whether you get some invariance of the classical invariance studied in representation theory. So maybe I would not explain. I mean, this is just a baby case. It's not appearing in the elliptic genus. You can make this calculation for P1 and all any Schubert varieties as well. Everything is accessible. Just specialize the general elliptic genus to this form. Okay, and that's. Thank you.